Okay, so next thing is uh, few results. And these results are proved in examples. Okay, and first is, if lambda is eigenvalue of t, then if lambda is eigenvalue of t, then first part, lambda raised to the power k is eigenvalue of t raised to the power k. Second part, alpha lambda is eigenvalue of alpha t of alpha t. For this is k belonging to natural number. So when you combine this thing, you say p lambda is eigenvalue of pt, where px is a polynomial. So what I'm trying to say is, for example, you have px is equal to a naught plus a1x plus to so on a n x raised to the power n. Now when I say that 1 is eigenvalue of I, then I say lambda is eigenvalue of t, then I say lambda square is eigenvalue of t square, up to so on lambda raised to the power n is eigenvalue of t raised to the power n. Done. Then you multiply this thing by a naught, multiply this thing by a1, multiply this thing by a1, multiply this thing by a2, multiply this thing by a2, multiply this thing by an, multiply this thing by an. You add them. When you add them, it will obviously become, this is a naught a1 lambda a2 up to so on an lambda n. So this is p lambda is eigenvalue of this is obviously pt, hence your theorem. So this is one result, we will use this. Second is 0 is eigenvalue of capital T if and only if T is singular. 0 is eigenvalue of capital T if and only if T is singular, i.e. all eigenvalues of capital T are non-zero if and only if T is non-singular. If and only if T is non-singular. I hope this thing is clear. To you. So for this thing, if lambda non-zero is eigenvalue of T, then lambda inverse is eigenvalue of T inverse. Fourth is if lambda is eigenvalue of capital A, this can come in 2 marks. Okay, then A determinant by lambda is eigenvalue of adjoint A. Perhaps we know that this lambda is non-zero. I hope this thing is clear to you. Now why we are doing this thing? Because we want to prove a theorem, and theorem will come after 5 minutes. Okay, one more result. This is 1 2 3 4 5 Cayley-Hamilton's theorem, the most important. And please do its proof also. I am not doing this proof, its proof, because you have done this proof in first sem and sixth sem. So I am not doing the proof. Please do it by yourself. And this is a very small proof. You can do from BSc first semester book or sixth semester book or from MSc book, up to you. Okay, it says that every linear operator operator satisfies its characteristic equation. Characteristic equation. Every linear operator satisfies its characteristic equation. So you say, i.e., if t from v to v is a linear operator, if t from v to v is a linear operator, comma, and delta lambda is equal to 0, be its characteristic equation. This is representation of characteristic equation. Delta lambda is equal to 0 is representation of characteristic equation. Be its characteristic equation, then theorem says that this polynomial equation will be satisfied by t also. Every linear operator satisfies its characteristic equation. This means then delta t will be equal to 0. Then delta t is equal to 0. Now I hope you remember this concept of order of element. Order of element says minus 1 raised to the power 2 will be equal to 1. But you say minus 1 raised to the power 100 is also 1. You say minus 1 raised to the power 1000 is also 1. But 2 has a property which all of these numbers do not have. The property is this 2 is least. So when you talk about order of element, then you say that a raised to the power n should become identity and this n should be least. And this n should be least. So you say order of a is least positive number, positive natural number you can say, or positive integer you can say, such that the element when raised to power becomes identity, and obviously the order of element is unique. So why I am doing this thing, I want to say one more thing. You have done that thing in number theory in which you say primitive roots. Primitive roots in number theory you have done. It says that we have a theorem. Theorem says name of theorem is Euler's theorem. Euler's theorem. Euler theorem says if a comma n GCD is 1, then a raised to the power phi n will always be congruent to 1 mod n. This is your result. This is Euler theorem. Now what we say? We say that whenever a will be raised to power phi n, it will surely become 1. But there may exist some power which is obviously less than phi n. This h is less than phi n. Still it makes a raised to the power h congruent to 1 mod n. So you say order of element modulo n. Order of element modulo n. You say order of element modulo n is the least power. We say that whenever we will raise power phi n, it will surely become 1. But we say that when we raise this a to some power h which is less than phi n and it becomes 1, we say the least power which is raised on power a so that it becomes congruent to 1 gives us order of element modulo n. From this we get primitive roots with respect to n. Primitive roots with respect to n. Primitive roots with respect to n is that a which is co-prime with n, and when you raise a to power phi n, this will become 1 modulo n, but no other power which is less than phi n will make it 1. What I am trying to say is a is said to be primitive root of n, or you can say a is said to be primitive root congruent n if order of a is phi n modulo n. You have done this thing. Why I am doing these things? number theory or group theory in linear algebra, because we want to define one new thing. This thing is called minimal polynomial. Minimal polynomial. What is the meaning of minimal polynomial? Minimal polynomial says that whenever you have a linear operator, Cayley-Hamilton theorem guarantees that the characteristic equation will be satisfied by the linear operator always. Now, what we want to do, we want to find a polynomial of least degree, which is satisfied by t from v to v. Okay, a polynomial of least degree which is satisfied by t from v to v. We represent it by m lambda is equal to 0. You can say if it is polynomial equation, then it will be equal to 0, otherwise it is m lambda only. So you say that first you have a linear operator, then you find the characteristic equation, then Cayley-Hamilton theorem says that this characteristic equation will be satisfied by t. Now next thing is we want to find a minimal polynomial for this linear operator capital T, which is also a polynomial, but its degree is least, in the sense that this is a polynomial of least degree which is being satisfied by capital T, i.e. mt is equal to 0. Polynomial of least degree which is satisfied by t. Okay, and it is clear remark is very clear to you that degree of m lambda will always be less than or equal to degree of delta lambda. Will always be less than or equal to degree of m lambda of delta lambda. Okay, in many linear operators, for example, characteristic equation is of degree 3. For example, characteristic equation is of degree 3, and when you find the minimal polynomial, its degree is 2. In many cases, if characteristic equation is of degree 3, then minimal polynomial is also of degree 3. So what I am trying to say is, in some cases, this is remark 1 and this is remark 2, in some cases minimal polynomial is characteristic equation himself or itself, whatever you say. I hope this is clear to you. Now listen to this. This is a remark. Remark says, this is not in your book, I am stating this thing. All distinct factors of delta lambda will be there in m lambda at least once. Okay, now this is also a theorem. You can say this is also a theorem. This is not in your book. I am defining this. All distinct factors of delta lambda will be there in m lambda at least once. Okay, please for 1 second remember this thing. Okay, this will appear in the I think in triangularization or diagonalization. This result will come, but if you understand this line for 1 second, if you take it as granted for 1 minute. Okay, now what I am trying to say is, you have that example 18. Example 18 says pxyz is 2x plus y, y minus z, 2y plus 4z. I think this is, you remember this example. Now you found the delta lambda. Delta lambda came out to be lambda minus 2 square into lambda minus 3. I hope you remember this, negative sign was along. Now what this very strong result says, this result says that minimal polynomial, in minimal polynomial, every distinct factor of delta lambda will appear at least once. So what you are trying to say here is that minimal polynomial will have lambda minus 2 and lambda minus 3, or lambda minus 2 square into lambda minus 3. Now you tell me, is this clear to you or not? Yes, Raghav, is this clear? First you find the characteristic equation of any linear operator which is given. Now, when you factorize this thing, this delta lambda, you will be having distinct factors in that. You have lambda minus 2 square, lambda minus 3. For example, there is a linear transformation from r cube to r cube, and when I find its characteristic equation or characteristic polynomial, it comes out to be, for example, it comes out to be lambda minus 1, lambda minus 2, lambda minus 3. Now, from this delta lambda, we want to find the minimal polynomial, and this theorem says, we will do proof of this theorem also. Okay, this theorem says that minimal polynomial will have every distinct factor at least once. So you ask this characteristic polynomial, who are the distinct factor that you have? It says lambda minus 1. So lambda minus 1 is distinct factor, it will be there. Lambda minus 2 is distinct, it will be there. Lambda minus 3 is distinct, it will be there. So you see that in this case, minimal polynomial is equal to characteristic polynomial. We do not have any option of removing a factor which is distinct from the other. We cannot ignore any factor which is distinct from the other. So you have to take lambda minus 1, you have to take lambda minus 2, you have to take lambda minus 3. Since you have to take all three, or even if it has lambda minus 10, it is distinct from the other factors, you will have to take lambda minus 10 in the minimal polynomial. So all the factors of characteristic polynomial are distinct, it will be there in minimal polynomial, and hence the minimal polynomial will be equal to the characteristic polynomial. I hope this thing is clear to you. Now here you have a factor which is repeating itself, lambda minus 2. Now this result says that minimal polynomial will have every distinct factor at least once. So you say, one second,